Hello everyone. So today we continue our learning the basics, and as you know, we're still in the chapter of pressure. So today we're going to learn about pressure in liquids. But before we start, let me to tell you the standard competence. Standard competence 3.8 describe the pressure and its application in everyday life, including blood pressure, osmosis, and transport tissue capillaries in the plants. Alright, in the previous lesson, we have learned that solid exert pressure, right? I have a question for you. Do liquids also exert pressure? Yeah, the answer is yes. Liquids also exerts pressure. Okay, let's see how liquid exerting pressure by doing a simple experiment. Take a plastic bottle is filled with water and make some holes into it. You can see the water is coming out, but why the water is coming out? Because the liquid that is the water in the bottle exerts pressure in all directions of the bottle. That is why when you make some hole into the bottle, the water was coming out. So we can say like this: liquid exert pressure against the surface they touch. In liquids, molecules are constantly moving in all directions and colliding with each other. Now we talk about hydrostatic pressure. The hydrostatic pressure is the pressure exerted by a fluid at equilibrium at any point of time due to the force of gravity. The hydrostatic pressure is determined by three factors. The first one is affected by density of liquid. Let's take a look at the figure. A hole is made at same height on the side of each of two similar tins filled with water, while the other one is filled with cooking oil. It is found that the jet of oils falls nearer to the tin and flows slower than the jet of water. Although both tins contain equal amounts of oil and water, this shows the oil pressure is less than the water pressure. Therefore, the pressure of liquid increases with density. So we can say that the bigger density of liquid, the bigger pressure will be exerted. Alright, so the second one is affected by force of gravity. Liquid with a larger force, if a gravity will exhibit a larger pressure, if other factors remain the same, because the higher force of gravity exerts higher pulling force on liquid, hence causing the liquid becomes heavier. For example, the pressure at a particular depth and liquid on the surface of Moon is 1/6 of the pressure of the same liquid on the surface of Earth. So we can say the bigger gravitational field strength, the bigger pressure will be exerted. Okay, the third is affected by the type of an object in the liquid. Let's take a look at the video first. The demonstration is carried out by filling a graduated cylinder that has three side openings with water and observing the speed with which the water exceeds through the three openings. The weight of the liquid causes a pressure in the container. As a result, the water spurts out furthest and fastest from the lowest tube away of each hole. This shows the liquid pressure increases with the depth. In other words, we can say the depth of liquid, the greater the weight above, and so the higher the pressure. Alright, from the three factors, it can be concluded that hydrostatic pressure depends on the density of liquid, gravitational field strength, and depth. This also means pressure is proportional to the density of liquid, gravitational field strength, and depth. And this can be written as P equals to rho g h, where P, pressure, the unit is Newton per meter square or Pascal, rho is the density of liquid, the unit is kilogram per meter cube, g is gravitational acceleration, the unit is Newton per kilogram or meter per second square, h, the depth of object in a liquid, the unit is meter. Alright, let's solve this hydrostatic pressure problem. The diagram shows a fish in the water. The density of the water is 1000 kg per meter cube. Determine the pressure exerted by the water on fish. So from the diagram, the depth is 2 meters. And the density of water is 1000 kg per meter cube. And we know the gravitational field strength is 10 newtons per kilogram. So by using the formula of hydrostatic pressure, P equals to rho GH, so we can substitute P equals to 1000 kg per meter cube times 10 newtons per kilogram times 2 meter. So P equals to 20,000 newtons per meter square, or P equals to 20,000 Pascal. Therefore, the pressure exerted by the water on fish is 20,000 Pascal. Okay, now we talk about the hydrostatic law of pressure for the static fluids. Let's take a look at the figure below first. I have a question for you. What is the pressure at the points A, B, C, and D? Okay, as we can see, all points are at the same depth. So therefore, we can say all points have the same pressure, right? That's known as the law of hydrostatic pressure. The law of hydrostatic pressure states that the pressure at a certain depth in the static fluids is the same at all points at that depth. Communicating vessels. Who hasn't yet experienced that fact that it's particularly easy to spill from a very full teapot or watering can? The reason is that the water in the spout is at the same level as the water in the rest of the can or pot. If you tilt the can, the water level remains in the same horizontal plane. So to spill it out, you only have to tilt the can a little. So, teapot or watering can are examples of application communicating vessels in our daily life. Alright, to know more about the communicating vessels, let's take a look at the video first. The surface of the liquid remains always at the same level horizontally in each of the vessels, no matter how the vessels are formed or how they are tilted. Every spot in the vessel is subjected to the pressure, which is caused by the weight of the water lying on the top of it. The pressure only depends on the depth. In order to maintain an equilibrium in the entire vessels, the same pressure has to be exerted on every point in the water column in each of the three vessels. This concept is known as the concept of communicating vessels. Okay, let's take a look at the figure. That's the liquid in U-shaped tubes. A U-shaped tube is a glass tube with a U shape. If we can see in the figure, a U-tube is filled with two different kinds of liquid, so the surface level of the liquid on both legs of the tube are different. But we know that the liquid pressure in A and B are same, right? So we can write PA equals to PB. And we know that P is rho times G times H. So we can substitute PA and PB. Rho 1 times G times H1 equals to rho 2 times G times H2, where rho 1 is density of oil, rho 2 is the density of water, H1 is height of oil, and H2 is height of water. So from this equation, because G is constant, so the equation will be rho 1 times H1 equals to rho 2 times H2. If we can see in the formula, we can use U-tube to compare and measure the density of liquids. Alright, let's solve this U-tube problem. Figure above shows a U-tube filled with water and liquid P. Liquid P is insoluble in water, given that the density of water is 1000 kg per meters cube. Find the density of liquid P. Alright, first we can write H1 is 10 centimeters, H2 is 12 centimeters, rho 1 is 1000 kg per meters cube. So we have to find out the rho 2. So by using the formula, rho 1 times H1 equals to rho 2 times H2. So we can substitute 1000 kg per meters cube times 10 centimeters equals to rho 2 times 12 centimeter. So rho 2 equals to 10,000 divided by 12. So therefore, the density of liquid P is 833 km per meters cube. Now we talk about the application of pressure in liquid. 1. Construction of dams. If you can see in the figure, the water at the bottom of the dam is at a higher pressure than at the top. Hence, the wall of the dam has to be thicker at the bottom to sustain the greater water pressure. The generator is placed at the lower part so that the pressure of the water is high enough to drive the turbine. 2. Thick wall built in a submarine. The deeper the submarine submerged into the water, the greater the pressure exerted. The submarine is built with thick wall to withstand enormous pressure at a greater depth. 3. Measuring blood pressure. When measuring blood pressure, the inevitable cut of the sphygmomanometer should be at the same level with the heart so that the pressure measure is equal to the blood pressure of the heart. Alright, I think that's enough for today. God bless you.